In this video, I'm going to talk about the allotropes of phosphorus. Phosphorus exists as a wide variety of different allotropes. Probably the most familiar to you is going to be red phosphorus. Red phosphorus is the red stuff on the tip of a match. And you can see down here, I've drawn out the structure of red phosphorus, or more to the point, I've copied in a picture of the structure of red phosphorus. And you can see that it is what we would call a network solid. So a network solid is a repeating pattern similar to a polymer where we just have an extended network of phosphorus atoms all connected, obeying the octet rule, and generally our chunk of phosphorus is almost like one giant molecule. There is an allotrope of phosphorus that does have discrete molecules, and that is white phosphorus. White phosphorus has the molecular form P4, and in order for all four phosphorus atoms to obey the octet rule, what winds up having to happen is they all have to have 3 bonds and 1 lone pair, and so you wind up making this cute little tetrahedron in which each of your 4 phosphorus atoms is connected to all 3 other phosphorus atoms in the molecule and also has a lone pair on the outside. Phosphorus is another essential element. The body uses phosphate groups to some degree as an energy currency. You will learn about things in biology like using ATP as an energy source and breaking off a phosphate group, leaving behind ADP. The TP refers to triphosphate. The DP refers to diphosphate. In the case of ATP, we're talking adenosine triphosphate, but there are other similar energy systems within the body based on the other nitrogenous bases. Phosphorus also has a bit of a tragic history in that back in the days when matches were made by hand, the workers in those match factories oftentimes got a condition referred to as phossy jaw because their exposure to phosphorus fumes actually effectively dissolved the bones in their jaw. And so another example of why it is important that we have laws to protect our workers so that the job that they're doing doesn't dissolve their jaw right out from under them. In the halogens section, we addressed the reactions of halogens with phosphorus, and I introduced this idea that the phosphorus exists as P4 if it's white phosphorus. P4 is the most reactive form of phosphorus, which really shouldn't come as any great surprise when we remember what that structure looked like. Remember, we had that tetrahedron or triangular pyramid shape here, with each of the phosphorus atoms having a lone pair as well. Well, if you do the math on what those bond angles have to be, it's kind of hard to tell because I can't draw that well, but each of these bond angles would have to be approximately 60 degrees. Now, if we were to apply VSEPR theory to each of those phosphorus atoms, they are each in the tetrahedral electron group family. And since they have 1 lone pair, we would be looking at trigonal pyramidal molecular geometry, and therefore we would be looking for bond angles that were a little bit smaller than 109.5 degrees, 109.5 being the right bond angle for a tetrahedral molecule, but the lone pair takes up more space and squeezes the bonds together, but it doesn't squeeze them as closely together as 60 degrees. P4 is highly strained. Those bond angles are much smaller than would be ideal, and as such, it is a very reactive material.